Sugar derivatives. Okay, we've already seen that you can take an aldose, for instance glucose, and oxidize it. So if you have a reducing sugar, it will oxidize, it becomes oxidized. And it reduces the metal. So we talked about this the other day. All right, so again, I'm not worried about stoichiometry. If you take your silver +1 or your copper +2, these metals can be reduced to silver metal and a copper 1+ ion respectively. And in the process, you oxidize the aldehyde to the acid. And again, what you've got here is, all right, glucose. And the suffix that we use for this is onic. So drop the OSE and this becomes gluconic acid. Okay. And what we're doing here is we're oxidizing at the C1 position. All right, so my aldehyde gets oxidized to the acid. Now this can cyclize and actually form an ester. So the hydroxyl on the 5th carbon again is going to attack that carbonyl with loss of water. Okay, so again this can go both directions if you lose water, and I'm going to make this into an ester. Okay, so notice that the number 1 position is got a carbonyl on it. So this is gluconic acid in a cyclic ester, which is known as a lactone. So I've got a cyclic ester, which is a lactone, and so I have gluconolactone. Okay. So that's oxidation at C1. We can also oxidate at C6. So we're going to do an oxidation at C6. Okay. Now, if I oxidize at C6, so oxidation at C6 right here, we learned in our organic chemistry that if you oxidize a primary alcohol under harsh conditions, you oxidize this all the way to the carboxylic acid. So at number 6, I'm oxidizing that primary alcohol all the way to the carboxylic acid. Okay. Now, I want you to think about organic chemistry for a moment. Okay, so this is a little side note. Okay, so if I take a primary alcohol and oxidize it under harsher conditions, like a chromium reagent, we learned lots of chromium reagents, this goes all the way to the acid. Now, an aldehyde can also be oxidized to the acid. So in fact, the alcohol passes through the aldehyde as an intermediate on the way to the acid. So let's write this all out again. We go from the alcohol to the aldehyde to the acid. Okay. This is an easier step. The aldehyde to the acid is an easier oxidation. This is a more difficult, this is harder. Okay, so the point is, if I've got something in here that's sufficiently strong to oxidize the primary alcohol to the acid, it would also oxidize the aldehyde. So the only way that we can oxidize this primary alcohol to the acid and not oxidize the alcohol is if this is an enzymatic oxidation. This has to be an enzymatic oxidation. Okay. So again, we'll just say that this is enzymatic. And again, the reasoning is that the aldehyde is more easily oxidized to the acid than the alcohol. And if I've got something in here strong enough to oxidize that primary alcohol to the acid, I would also expect this to be oxidized as well. On the enzyme, it's locally, and so I'm going to be able to oxidize that on the enzyme. Now, if this is glucose, okay, the suffix that we have here is uronic. So drop the OSE and add the uronic, glucuronic acid. So again, we've got the onic suffix, the uronic suffix. So onic is at C1, uronic is at C6. Okay. Now let's oxidize at both C1 and C6. So if I were to use a chemical oxidizing agent, it would, again, oxidize both of them. And that's what we're going to see here. So under harsher conditions, I would expect to oxidize both. So here's the acid at the number 1 position and the acid at the number 2 position, or number 6 position, excuse me. Okay, so again, this is glucose, and I'm going to oxidize at C1 and C6. So both of those get oxidized, and the suffix here is aric. So drop the OSE, and this becomes glucaric acid. Okay, so again, the suffix aric means that you're C1 and C6. All right. So let's take, for instance, if you've got any generic aldose, if you oxidize at C1, you've got an aldonic acid. All right. If you oxidize at C6, you have the uronic suffix. So this is an alduronic acid, starting generically with any aldose. Again, if you want to put in a particular sugar here, mannose, you would have a mannonic acid, okay, etc. If you oxidize at C1 and C6, this gives you the aric. So this would be an alderic acid. Again, generically. So you have these suffixes that tell you what the oxidation is. Let's look at reduction. Now in reduction, you can use your lithium aluminum hydride or your sodium borohydride, again, as a source of hydride. This is the weaker. This is actually sufficient for our purposes. Okay, so let's take our glucose. And if I reduce this with the sodium borohydride, I'm going to reduce that aldehyde to the primary alcohol. Okay, so the primary alcohol gets reduced, the aldehyde gets reduced to the primary alcohol, okay, and the suffix here is etol. Okay, So again, if I have glucose, drop the OSE, and this becomes glucitol. Okay. In fact, we don't use the word glucitol. If you take sorbose and reduce it, you get the same molecule, and so we call this sorbitol. I don't know why, but that's the name of it. Now, again, you'll notice this itol suffix. So if I had an aldose, I would have an alditol if I generically reduce this. If you look at the label on some sugarless gums and candies and mints and things like that, you'll find these itol. You'll find xylitol, sorbitol, and as examples of those. So your sugarless gums and candies will incorporate these reduced sugars. Now, when they say sugarless, don't get confused. They are not telling you that it is calorie-free. This, you can still metabolize this. Okay, and there's lots of energy in this, but those bacteria on the surface of the teeth that polymerize sugar to make your dextran don't incorporate this. So again, this is again recommended for your sugarless gums and candies because the bacteria in your mouth don't utilize this to produce that dextran polymer, the plaque. Okay. Continue with sugar derivatives, amino sugars. Okay, and amino sugars, what we do is we replace the number 2 position with an NH. Okay, so again, I'm going to do glucose here in the cyclic form for you. All right, and so this is glucose. And to convert it into the amino sugar, you're going to have an NH2 at the number 2 position. So amino sugars usually put the amino at the position 2. So if this were glucose and I replace the hydroxyl at the 2 position with the amine, this becomes glucosamine. Okay. And sometimes you will find these acetylated. So sometimes the amino group gets acetylated. All right, so if you have an acetyl group, you would add that and replace it with one of the hydrogens, okay? So this would produce NAG, N-acetyl glucosamine. Okay. Deoxy sugars. There's really only one that we want to look at here. If we look at ribose, now in the linear form, ribose has got 5 carbons and all the OHs on one side. Okay, and generally, again, if this were to cyclize, you'd expect that to make a 5-membered ring. Again, this can be either up or down. So this is your ribose. And usually if you have a deoxy sugar, again, there's always exceptions, usually at the number 2 position. Now, there are some other deoxy sugars that you can see in textbooks where the deoxy is at the number 6 position. This is the only one we're going to be talking about because you're familiar that ribose is used in RNA and deoxyribose is used in DNA. So there's no hydroxyl at position 2. So this is your deoxyribose. that, again, ribose is used in RNA and deoxyribose is used in DNA.